Good day, my name is Dennis and I will be your event specialist today. At this time, I would like to welcome everyone to the Introduction to Additive Manufacturing and Common Pitfalls web conference. All lines have been placed on mute to prevent any background noise. Please note that today's web conference is being recorded. We will have a question and answer session at the end of today's presentation. However, you may submit questions at any time. Locate the Q&A option in the floating toolbar at the bottom of your screen. Click on the Q&A icon to open the Q&A panel on the right-hand side of your screen. Type your question in the open area and click Send to submit. If you experience any technical difficulties during today's conference, please use the chat box to speak with me directly. Locate the chat option in the floating toolbar at the bottom of your screen. Click on the chat icon to open the chat panel on the right-hand side of your screen. You can also press *0 on your telephone keypad to be connected with an operator. It is now my pleasure to turn today's program over to Chris Barrett, President and Founder of 3D Directions. Chris, the floor is yours.
Thank you very much, Dennis. Everybody, welcome. It's a pleasure to have you all. We were looking forward to this lecture for a good couple weeks now. There are a couple quick questions that have popped up, and the first one I'm just going to address right now, and that is we're going to go ahead and get started. This lecture will be recorded and can be referenced later. And as far as the audio, you're going to need to use a telephone instead of your computer. All right, but I'm going to go ahead and get started. As was mentioned, my name is Christopher Barrett. I do a lot of consulting for small and medium-sized businesses, mostly those that are interested in getting into the additive manufacturing sphere. And with that, we're going to go ahead and get started. Today's agenda, we're going to talk a little bit about the beginning of additive manufacturing. We're going to go through and spend a good bit of time on the 7 different types of additive manufacturing and their likely headaches. We'll then talk a little bit about some of the colliding of the software and the hardware and those type of things that have benefited us recently, and then obviously follow the money question that everybody's most interested in. So in the beginning, 3D printing has actually been around for quite a while. CAD was developed back in the late 1950s, 1960s was its origin point. 3D printing started with 3D systems with stereolithography. A lot of people think it started with FDM, with fused deposition modeling, but it in fact did not. It started a couple years before then. 3D systems actually had to develop their own type of a file, and that was an STL, which you can see they started working with around 1987, and that was so they could slice the CAD files that we were used to working with to be able to slice them into layers and then thereby go on and 3D print them. Another common type that's out there is powder bed fusion, and that was developed by the Fraunhofer Institute in 1995, and binder jetting 1993. So what you're going to see is some of this technology has been around for quite a few years. Some of that means that it's mature, and some of it is not. And we're going to go through some of those common pitfalls and where you can kind of divide those lines today. The common question is, how new is this? Well, if you look at this patent from 1925, it was patented in April 14th, 1925. And the couple references out there, this was electron welding. If you look at the parts, you're going to see parts that look very similar to this today. He was welding to a metal base plate. That's a common approach today. And he was going up layer by layer to build his final design. Very similar. So the concept of what we're doing has been around for quite a while. So let's briefly start with the 7 types of additive manufacturing, and we're going to go through all of these one by one. Then we're going to take some time, we're going to slow down, and we're going to go back through them a second time so that we can kind of look at some of their pros and cons. The first type is material extrusion. It's what is most popular and well-known out there. The most common version of it is fused deposition modeling, FDM. This can either be done with a filament or recently they've been working on using pellet extrusion, where they will use an auger approach to extrude the pellets. So if you look at the picture in the bottom right with the creator bot, you can see some hoses faintly up there in the spools. What that's going to do is it's going to send the filament up and down through exactly like a hot glue gun used to work, or still does work. And it'll go through a print head that'll heat it up to the appropriate melting temperature, and it'll run it down in the path that what is needed to get the part. You'll see that there's quite a few different types of FDM printers out there. We have everything from the lovely Dremel system that you can buy at Lowe's all the way to the Stratus's 450 MC, and you get quite a range of quality, you get quite a range of different materials and stuff like that out of these printers, but they all have their place. And we'll go into some of that in the next time through. So the next type is binder jetting. This one, the easiest way to think about it is the old printers where it would run the inkjet cartridge back and forth on the belt system, and it would deposit the ink exactly where you wanted it to go, and you get your piece of paper with the print on it. Well, what they did was they swapped the ink and they instead replaced it with binder, so glue, and they'll spread a layer of powder and they'll glue it exactly where they want it using the drops of glue instead of ink. And they'll build it up layer by layer that way. Each time they will pass through that layer, they'll use a heat lamp or a UV light or something to cure the binder so it makes it semi-solid. When the part is finished, we'll tap out all the extra powder and retrieve it, kind of dig it out of the bed. And then we can take that finished part, that green state part, and put it in a sintering furnace, heat it up, center it to wherever is appropriate for the material that we're working with, and it'll cook out the binder and leave us with a largely dense part. It depends on kind of what you're working with as to how well it cooks out the binder, and there's different tricks and tips for those who work with these materials regularly that they've developed over the years. Another type that's very common with this approach is to do sand printing. And what they'll do that is for a traditional casting where they will print the mold, because we don't care about the sand and we don't care about the glue. Then I can do a casting back into that mold and smash the mold, get my part out. And it's a good, quick way to get a solid metal part. And that is a common approach today as well. So that's binder jetting. It's jetting of binder onto a material and a substrate. The next type is material jetting. So where this differs from binder jetting is here we're working with actually jetting the material that we're using to make our 3D printed part. So a common material used for this is wax or a photopolymer. The reason we'll use those is, again, an investment casting where I can print the part. I can then do a burnout cast and get a solid metal part afterwards. That was common. Waxes tend to work very well with kind of heating up and dropping it out with microjets. The X-Jet printer, which is seen on the left, they were actually using slurries. And so rather than going straight with the material, they're doing ceramics and they're looking at metals, and they will create a slurry and they will deposit through many microjets their material, and then they'll partially cure it. And same thing we had with the binder jetting, where you'll take your green part, you'll put it in your furnace, you'll then sinter your part and make it solid. The advantage of material jetting over binder jetting is you do not have a glue or some sort of substrate that you have to cook back out. You can go directly to the part, but it is more difficult to go directly at the part. And depending on which system you work with, the little nozzles can come up more or less easily. So maintenance is a huge issue with these printers. But they work very, very well with their designated approaches. So another type that's out there is stereolithography. That's kind of a sub-name under the vat photopolymerization, and we're going to go through the different types of vat photopolymerization later. This works where we have a UV curable photopolymer resin, and it's a liquid, and we will shine a UV light on it and cure it selectively. This works a lot like gel nail polish, which is commonly used where you, different people put gel nail polish on, they'll stick their hand under a UV light, it'll cure instantly hard and set up. So we're using the same thing, different approaches to hit that. Sometimes we'll use a laser, sometimes we'll use more of a TV screen approach where we're putting the whole image against it, and we'll go through those differences. Additives are often added to these resins, so we can do ceramics or metals, similar to the binder jetting where you have to then get the photopolymer back out to get a dense part, but still a very effective approach. And the next one is laser powder bed fusion. So this is one of the direct metal approaches that we have, and this is basically spot welding with a laser or an electron beam. So you'll have a layer that's spread of powder metal. Sometimes we'll do plastics, sometimes we'll do ceramics. We can tune our lasers to what type of material we're working with, whether we need a higher power laser or a lower powered laser, and we will melt or sinter each layer selectively and spread the next layer. The advantages to these approaches is we tend to be very good with lasers and getting the spot sizes quite small, and so we tend to have very good surface finish. You can see some of these parts down below. It also allows us to get very complex features that we would not normally be able to manufacture traditionally. So the sixth type that we're going to talk about today is direct energy deposition. So this is the one that's most commonly known to machinists because it's clad welding. And so we're going to build up our part layer by layer, just like we would with a MIG welder or a blown powder coming through the nozzle of the welder, and we'll work it up layer by layer that way. One of the exciting things with this type of approach is we're mounting heads. People are working on being able to mount the heads inside of typical CNC machines to do hybrid manufacturing with these. And so you don't have to move your build tray and out of the machine and back into the machine, which saves you a significant amount of time. But what you will see is if you look at the part on the left compared to the image I showed you from that patent of 1925, the part quality looks very, very similar. The only difference was this was controlled by a machine, and the other person had to do it by hand, building up each layer. All the rules with welding still apply. If you can weld the material, you can likely do it. If you cannot weld the material, you're still out of luck. So a very good approach, and we'll go through some of the pros and cons of this one later. So the last type that we'll talk about is sheet lamination, where we will use either a sheet of metal and work it up layer by layer, or we will use paper or foil or different types of things. Anything that you can get in a sheet form and lay out layer by layer and build up. Then you have to bind each layer together, and you can do that a couple different ways. You can use an ultrasonic weld to kind of fuse the different layers together. You can use an adhesive of some sort. There's a couple different ways to get at this. The M-Core systems are nice because you can color the layers as you go along, because there's no reason you can't have a colored ink head on your printer. And you can get a nice feature like our beautiful building here in the center, where you build that up layer by layer, and it's coloring each layer appropriately. All right, so we're going to now kind of take a 10,000-foot view on some of these pros and cons. It's really hard to go through all of the pros and cons of each type of type of printer in depth in a short version. So we're going to just kind of hit the tops of everything, and if you have specific questions, that would be something that we'd probably want to deal with offline, but we can try to answer some of them later. All right, so we're going to stay with the same graphic just for simplicity. All right, what is the difference with the FDMs printers, the first time I talked about, with the 100,000 version versus the 10,000 version, or the 1,000 version? And a lot of that comes down to two things. First of all, the more expensive versions tend to have heated chambers, and the heated chamber allows you to do a much wider variety of plastics. So the inexpensive one that we mentioned that you could buy at the hardware store or something like that can only really do one type of plastic well, and that's polylactic acid, or PLA, which has good uses, but it does not. It's known for being brittle. It's known for being more cheap. There's other uses you can use with it to kind of on an indirect approach to get to your final part, but usually you do not want your final part being out of PLA unless it's a prototype situation. The $100,000 version not only has a heated chamber, which allows you to hit higher temp plastics, the materials that make up the printer are usually more rugged to be able to handle those higher temperatures. The wires are coated to protect themselves so you don't melt your wires. And you can hit higher temperature plastics like Ultem. Ultem has been used in the aerospace realm as a cockpit safe material. And that's because its flame smoke properties as well as its outgassing properties have been recently qualified. The other thing you get with the $100,000 versions that are going to start showing up on some of the more inexpensive versions is dissolvable support. And compared to a normal part where I build it up, I'm dealing with plastic that I'm extruding out like a hot glue gun. I need to support my part in some sort of way, or everything's going to start drooping over. All my overhangs are going to dip. And so what you end up doing is building a raft with different layers of support as you build up that part. On the more inexpensive printers, you have one type of material and one nozzle, and so you have to get all those back out, which means that some poor soul has to sit there with a razor blade or a pair of scissors and cut all of those supports back off your part. Usually there's a little bit of a rough surface where they cut those off, so you'll take a Dremel or sandpaper and sand it back down. And so it kind of ends up being a little bit time-consuming. It's still faster and cheaper than making it traditionally because you're only making one, but not as handy. With the dissolvable support, a lot of those supports are water soluble, and so we can build it up, and I can take my part, I can throw it in a bath, and it'll eat off all the supports, and I can get my final part. I don't have to cut any support off. I don't have to sand anything. It comes off looking quite a bit more professional. So that is a huge upside to a more expensive printer, is the time that you save with each and every part. There's a variety of other small differences, and there's everything in between the cheap version and the expensive version, kind of picking what you want. And it really depends on your unique situation as to what type of printer you're looking. If you're a hobbyist, you want the more expensive one, inexpensive one. And if you're a professional one who's doing an architecture type setup where you show a final model and it has to look right, you're probably looking at the more expensive version. FDM, because of the way it's set up, it's easier to get larger build tray sizes. There are some systems out there that I did not cost on this that are they're called the BAM systems, Big Area Additive Manufacturing, and those are the ones where you see the 3D printed car. And so they'll 3D print the body of the car, and what they will do is they will reinforce their plastic with a chopped carbon fiber or something like that to be able to handle the structural load that they need to. But it's the same type of approach. It's just really kind of what you're hitting. So let's talk about binder jetting. I mentioned a little bit earlier one of the pros and cons. The pro is you can really hit any type of material with binder jetting. It's the quickest, fastest, easiest way to do a new material because you're just gluing it together and then you're sticking it in your sintering oven and sintering it in a secondary step. So as long as your oven and the size of your oven can hit the proper temperatures with the proper heat treatments, you're good to go. Downside is that binder, and wherever you had a drop of binder, you're then going to end up likely with a pore, and so you either need to compensate for that with your heat treatment, and so you're going to heat it up a little bit hotter and you're going to have a higher shrinkage rate, or you're going to have to back and fill the material with a softer material like a bronze and a steel, and it'll soak it up, and that way you have a fully dense part. Some people want heat exchangers, for example, that are not fully dense because they want them to transfer heat more effectively, and so they like the porosity. But for most people who are looking to directly print a part, and most people who are used to the machinist realm, it's not exactly what they're looking for. The sand printing where you do casting has really been taking off recently, where you take an indirect approach. So rather than dealing with the metal, is it dense, is it not, what are the specifications I need for my customer, I will simply print the mold, I will cast the part, I know what the requirements for the casting, I know what the heat treatments are, and I can do everything the standard flow. I just input a 3D printed mold. This does two things. The molds by themselves are typically slightly more expensive, but you can do a significantly more complex part. Because of that, you're able to take an assembly where you had 2 or 3 parts with some welding, and you're able to make them all into one or a more unique geometry. So binder jetting has a lot of good uses, kind of where you need your tolerances to be. So then we'll go some of the material jetting. Material jetting, you are likely dealing with, like I said, photopolymers or waxes. Recently, they've been doing ceramics, and they've been doing metals. The photopolymers and waxes have been developed for quite a while. They've been used for a long time with an investment casting approach to them, or the ceramics are relatively newer. The issue with, as I mentioned before, with most of the jetting techniques is you have very small nozzles, and you need to make sure that your material is not going to seize up in the nozzles. The binder jetting with the glue, you will typically run a cleaner through your machine, and that needs to be running pretty much nonstop anytime you're not printing. These aren't really machines, any of the professional grade machines, you can't really just turn off, walk away for a long time, come back, flip it on, and expect them to work. You're really needing to use them on a regular daily basis, or they tend to gum up, you tend to have problems, and it ends up being a little bit of a pain. They've got very good uses, but these aren't really machines that you're looking to, I want to use it every now and then as a hobbyist. These are more, I'm going to do this on a regular basis. This is going to be a major part of my business. All right, so the vat photopolymerization. So there's 3 common types of vat photopolymerization out there. These are all underneath that overall umbrella term. And that is stereolithography, digital light processing, and the continuous liquid interface production. Stereolithography is kind of some of the original technology where I would have my liquid vapor or liquid resin, and I would run a UV laser back and forth and kind of etch out my design. I would then raise the build tray up a slight amount and let fluid flow underneath it, and then I would laser out the next layer and do it layer on layer, building up from there. Digital light processing came along after that, and same with the clip technology. And those are very similar in the fact that instead of using a laser to trace out my layer, I'm going to actually project the entire image, and I'm going to do, for the digital light processing, snapshots of those images. For the continuous liquid production, they're trying to actually morph the image. And that one's fun to watch. If you can ever see the carbon technology online, where they just literally pull the part out of the vat, it's quite mesmerizing to watch. And you have different pros and cons of all these different approaches. With the digital light processing and the clip technology, you can hit some materials that you can't really hit with the stereolithography, but then there's always the argument going back and forth as to who has the better resolution and who has, who can hit what. The clip and the DLP have been around more recently. The SLA has been around since the beginning of 3D printing. They will add different additives to the photopolymer resin. So you'll add a ceramic. That's been a relatively new development, where they will do zirconia for dental implants and stuff like that. And this is a popular way to get to a ceramic, because I can cook out the resin and get a dense ceramic part. I do not know if they've been accepted in the U.S. to be able to use by the FDA yet, but I know that Europe is starting to use some of them. The other thing you can do with this is, just like with the wax printing for the material jetting, you can do those same type of resins here with SLA, not wax, but a photopolymer resin, where they will tune the chemistry so that when it burns out, it's a clean burnout, and where a wax, you'll have a little bit of a carbon left over, residue. This one will be a lot cleaner. Hobbyists tend to like these. You can get into casting a lot cheaper. You can make good quality castings for jewelry and stuff like that. It's a more quick and easy way to get into it, so you can get your mold built around it and just burn this out. Significantly easier than carving out a piece of styrofoam or something for a hobbyist. So powder bed fusion has two common approaches: laser powder bed fusion and electron beam melting. The differences between these two technologies is that the laser powder bed fusion is obviously using a laser. Because it is spot welding, you have to weld to a build plate. You need your thermal transfer of heat. A lot of your laser parameters are tuned to be able to transfer heat through the parts and through your supports. You do need supports with this type of approach. Same with the vat photopolymerization, you will need some supports to hold up your part. The metal, the supports take on two roles. One, to stand up the part, but two, to transfer the heat. So if you can imagine the FDM approach, where you have to take your razor blade or your scissors and cut all the plastic supports off, imagine doing that with the metal. Significantly harder. A lot of the skill coming into laser powder bed fusion and electron beam melting is learning to build your part well. So a lot of the skill is designing of the part, designing of the supports, and keeping in mind how you're going to get it all back off the build plate, what sort of surface finish you need. If you're going to have to machine this part already, do you want to make a part so you can just machine it easily? Do you want to guide your machine? There's a lot of different variables in there that you're going to have to keep in mind. The electron beam melting, what it uses is an approach where it'll partially sinter each layer, and the supports, the parts can be built on top of each other and almost be self-supporting, so you can fill up your whole build tray. Laser powder bed fusion, you can build the flat layer, but as soon as your build tray's used up, you can't really build parts above those without being really creative with your supports and that type of geometry. The electron beam melting, you can just, in this case, we have titanium hip implant cups. You can build multiple of those stacked on top of each other, and it tends to be very effective that way. Downside to electron beam melting is you're not going to be able to reuse your powder as much. Laser powder bed fusion, you can reuse your powder significantly, because if it's not melted, you can sieve it, put it back in the machine, keep on going. And there's more nuanced differences. Laser powder bed fusion machines tend to be a little easier to walk away from and come back a couple of weeks later and they work great. Electron beam tends to need a little bit more upkeep, but again, it depends on what type of facility you're working with, what's your ultimate outcome. And again, remember with all these approaches, if you're machining all these afterwards, there might be a keep it simple solution in there that could really help you out. So directed energy deposition. So we talked a little bit about this. This is where you're welding it up from the base plate. You're using either a glorified MIG welder, you're using blown powder. There's a couple of advantages that you have for this over a powder bed fusion system. First of all, if you are blowing powder or using a filament, you can swap the types of powder or filament that you're using partway through. So the part on the left I chose specifically today because we start with one material, that's the material that's a little closer to the base plate, and we transition into a completely different type of material. Now, there is a lot of work that goes into being able to transition a material from one to the other because you have, for those metallurgists out there, eutectoids and eutectics that drastically change your melt temperature. But the issue is you can actually do it. With the powder bed fusion, you load one type of powder into your machine, and it's very hard to switch from one to the other. There's a lot of research being done to be able to do this on a normal commercial scale, but on the large scale, it's not as easy. The directed energy deposition machines on the whole, though, are slightly behind the technology of the laser powder bed fusion. This is because mostly the research dollars, which we'll go into a little bit, have been geared towards powder bed fusion. Aerospace tends to be driving a lot of things right now. The other huge advantage of direct energy deposition is the fact that a lot of people are using these with traditional manufacturing. So if I have a CNC, I can mount a unique head inside of my CNC and swap it out with a tool and machine my part, build up a little section, machine my part, keep going. This also allows you to be able to do part repairs. So imagine a turbine blade that we had, and it's a $500,000 turbine blade, and it's worn through its life cycle. So that means that the fins are probably about a 1/4 inch smaller because they've been worn down on the end, and I need to grow those back out. With direct energy deposition, one of the goals is to be able to weld out each of those fins with an automated process and then machine them back down to tolerance. I might not have 50,000 hours of lifetime. I might have only 10, but a $5,000 patch versus a $500,000 new blade is a big difference. So there's different pros and cons that are going. One of the reasons I say the technology is a little bit behind is it is significantly harder to do the coding for this, where you control the robotics with different features and stuff that you want to be able to go by inputting your original STL. So there's a lot of good research being done out this. Lincoln Electric, I've been very impressed with their work, and I'm very excited to see where this one goes in the future. But there's some nuances that if you want to get into this technology that you should probably be aware of before you jump in with both feet. So the last one is the sheet lamination. And we talked a little bit about this earlier, so I'm not going to spend too much time on this. Your weakest point is your adhesive. So if I am ultrasonic welding these layers together, I've got to make sure that they're solid. If I am gluing the layers, the glue is my weakest point. So that's one of the things with this approach. It's often used in modeling. You can see the house on the left, and it looks great compared to what we had 10, 15 years ago. The advancements of being able to change colors has significantly improved. But depending on what you want to do, you're probably not going to be making commercial parts that you're going to be producing and selling on, and with any sort of mechanical properties that you have to hit with these. There's better approaches if you're going to go that route. All right, so one of the things that we need to keep in mind when we look at all these different types of printers is the colliding of software and hardware. So oftentimes what we're having is some sort of instigator. And one popular one recently has been the computer gaming industry, where they're trying to do games live, they're trying to stream games, and that leads to a need for better computer hardware because they don't want as much lag time. That often leads to better visualization software, which means we can do more with CAD. And then we get things like topology optimization. So you can see down below, this is a part I did where I took a basic bracket, I optimized it for my stresses, you reduce the material down to what I needed, and then I redrew the part with the optimized geometry. This is one of those common misconceptions between the people who do regular machining and those who do mostly 3D printing. The optimization software will output an STL. It's a mesh that you have to work with. That is not an IGES file. That is not a step file. That's not something I can really put into my CNC and machine back out. That means I have this complex geometry that I then have to go back through and hand draw in CAD. So that part down there for one part took about 35 different planes compared to the part that I started with where I really worked it off of, the basic planes. I didn't have to do much with it. Another thing you run into, so saying that, you need to keep that in mind that just because I can get a mesh of an optimized part doesn't mean it's CAD. There's some more steps in there. The other thing you need to keep in mind is maybe I don't want to do all of that optimization. There is classes that you can take on just topology optimization and how much you want to do versus not. And a lot of this comes into the thought with 3D printing where you need to have the whole life cycle approach of how you're going to build this part in mind. I need to know, am I going to have to final machine this? If I'm going to have to mount this on the CNC at the end of the day, maybe I don't want to do as many steps in the middle because it's good enough. And if I've already got it in the CNC and I'm already milling it, it's cheaper to keep doing that. Maybe I do want to optimize things. The weight reduction might be worthwhile. It might not be worthwhile. So that kind of leads us into the follow the money conversation. Aerospace and biomedical have been some of the large leaders for this industry, mainly due to cost, and that is they're willing to pay more for an expensive, unique, complex part. The other things that people are doing are hobbyists with rapid prototyping, automotive, NASCAR. Anytime you need a low volume production, 3D printing tends to be viable. There are graphs and stuff we could go over where you can see if I want one part, I could 3D print it. If I want 5 parts, I could 3D print it. 10, maybe, maybe not. 100, probably I'm going to be looking at traditional manufacturing. And anytime I'm over 1,000 or more, most likely I'm looking at traditional manufacturing, unless it is an aerospace or biomedical part where I need the complexity. So the hip implants are a great example of a part that I would want to 3D print. I need that mesh so that the bone can actually grow into the mesh and kind of become one with the body. Or I want an aerospace part where it's optimized and lightweighted because of the fuel cost savings. So it kind of depends. The other thing that's going on is a lot of these patents are expiring now, which means that competition is slowly driving down costs. One of the things you're going to need to be aware of, though, is your material costs to do the different types of 3D printing might be really high compared to traditional manufacturing. It is cheaper to buy a large block of material than it is to buy powdered material of the same volume that had to be gas atomized. That is usually a 10 to 100x cost difference between the block of material and the powdered material. So just in that alone, your stock material means that it's probably very much more cost effective to machine your part traditionally, if you can, than to 3D print it. So the other thing I like to look at, kind of show people, is the stock market. little bit. I am not a financial expert by any means. I do not claim to be. But I love looking at the graph where about 2014, January 2014, everything started crashing in the 3D printing realm. And you had a couple things going on. First of all, some of the major companies started reinvesting cash to be able to expand their capabilities. They started buying up smaller companies. So that started burning through things. But you also had a realization in the community that 3D printing is not going to replace traditional manufacturing. It's going to augment traditional manufacturing, but for a one-to-one comparison, if I'm making it's faster to do 3D printing. If I'm making 1,000 parts and I'm comparing FDM versus plastic injection molding, it's not even a fair comparison. The cost and the speed of standard injection molding is by far the way to go. The stocks have since kind of evened out a little bit, but what people are finding, especially in the machinist realms, is there's a lot of indirect approaches that we can take that really give a lot of benefits to the overall industry. And so sometimes it's not, the goal isn't to directly print your part, it's to come at it from a little bit of a indirect angle. So, like I said, this is a complement to traditional manufacturing. We are not replacing it in any stretch or imagination, but it's definitely a good complement. And with that, I think we're going to start wrapping up. Do we have any questions out there? If you want to type them into the queue, I'd be happy to answer them.
And once again, as a reminder, everyone, you may ask a question through your web console. Locate the Q&A panel on the lower right-hand side of your screen. Type your question in the open area and click Send to submit.
Which process? Okay, I have a good question. So Eric says, in my opinion, which process do I think will be the most popular in the coming years? It really depends on which industry you're talking about. I think with the machinist and the typical machine shop approach, given 10 years into the future, I have good hopes for the hybrid manufacturing approach. I believe aerospace is extremely invested in the laser powder bed fusion. I don't think that's going anywhere. So it really depends on what your industry, if you're hitting plastics. You're probably looking at stereolithography. All right, so what about shot molds? Sorry, I've got a couple different questions here. What about shot molds for injection molding? So shot molds, that's a tough one. It really is going to depend on your surface finish that you're going to need at the end. Laser powder bed fusion is probably going to be your best approach to get there, just because it's got the best surface finish. Electron beam melting is a little bit rougher, and direct energy deposition is rougher still, but that kind of depends on the complexity of what you're working with. What is the cheapest method to get FDA quality parts? That one is definitely a complex issue. If we're talking medical grade implants, I know titanium has already been used by quite a bit. If you're talking the ceramics, it's really kind of dependent upon the FDA, and it's hard for me to judge that one. Typical cost of titanium 6 powder per pound. Titanium is a good metal to print. It's well known in the aerospace industry. The cost depends on if you have to buy it from your OEM for a specific, application that's certified, or if you can get anybody off the shelf. I'm going to answer you in kilograms so we can double it. Or half it. It's $250 to about $500 a kilogram. So it's very expensive right now, and it recently jumped. So we'll see kind of what that happens. So there's another question: will advanced sensing, will the in situ monitoring and stuff affect the industry? And yes, as that starts developing, the industry will, the quality control from your standard companies like ASTM, NIST, all those are working with OEMs right now to develop those standards. In situ monitoring is a huge aspect of that. One of the reasons is spotting defects and spotting what is a rogue defect, how big do we care, when does it become just an anomaly, or when does it become a defect? And that realm, there's a lot of research being done, and it's one of the reasons why we don't have a lot of normal shops doing 3D printing for aerospace parts, because the big companies like Boeing, Honeywell, Lockheed Martin, those guys are still trying to develop what is good and what is not. Another question, I'm not going to get to everybody's questions today. I can see based on how many are popping up, and I will try to get some answers out later. But one of the questions was high temperature alloys for laser powder bed fusion. I know we can do the Inconels quite regularly. Inconel 625 and Inconel 718 are standards. There is development going on in other materials as well. Some have been released depending on which company you go with or not. It's kind of a material-specific question. Most of these, if you want to get the powder and you want to develop the laser parameters yourself, you're welcome to. But if you want to then sell that part to Boeing or Lockheed or someone like that, you're going to have a lot of qualification issues you're going to have to go through. So another question was, what about food contact? Food contact depends on the material you're working with. You're going to need a material that is already food safe. So some of your plastics can be qualified for that. Some of your metals, not others. And what you're going to have to do is make your whole environment safe, just like you would a kitchen, and you're going to have to work it through. So there's going to be different standards that you're going to work with that. But that's kind of a broad question, but it depends on what you're doing. There are people who interact food with different materials. If you're Hershey's, you're going to start 3D printing chocolate. So, there is that. The low volume CNC metal parts, the best bang for your money, that's a great question. It's really dependent on if you are going, how much optimization you're doing, and what tolerance, what surface finish do you need. Most of these techniques are not good with building threads. So if I need something with a nut and a bolt type situation, most of these approaches, you really need to machine them afterwards. So that is a huge defect. Now, they're making advances in that realm, but on the whole, threads tend to be a little bit difficult unless you're talking a large thread and the little variations aren't as much of an issue. What is the most needed material in the material extrusion space? The biggest material being used is PLA by far, and that is because the cost of making the printers. So because I don't need to heat the build chamber and all the hobbyists can use it, PLA is by far the largest per volume. As patents expire, I would expect that to change a little bit, but that's by and far the most, just because the most types of printers can use that material for material extrusion. What would be the first steps for someone that wishes to explore 3D to replace traditional IM parts? Really, first steps would be identifying what materials, what tolerances you need, what type of strength. That's going to drive what type of 3D printing you can then explore. which will then drive how much it's going to cost to get into that space. So you need to keep in mind that if you can traditionally manufacture this part, it will probably be cheaper to do that depending on the complexity and the small volume and all that. So there's some nuances in there. But so if we're talking a metal part that I have to CNC, and I'm talking laser powder bed fusion where I have to spend $250,000 or more just to buy the machine, plus double that for what you'll need for your workspace and the extra stuff, you could easily be in for a couple $1 million just to get up and running. And that is not an inexpensive approach at all. Last question, and then we're going to wrap this up. Is the speed of the DLP clip printing limited by the polymer chemistry alone? It is not limited by that alone. It's also limited by the intensity that you can go and what resolution you need. If you need a high resolution, you typically go slower. If you need, it can be a little rougher, you can go faster. One of the big advantages to using a vat polymerization method is the surface finishes in general are very smooth because you're dealing with a liquid. So I'm going to go ahead and wrap things up, and then we'll try to get more questions out later. So Dennis, hand this over to you.
Thank you, and thank you, ladies and gentlemen, for joining today's web conference. This does conclude today's call. You may now disconnect.